Hi there, my name is Sharbil Tok. I am an Associate Research Fellow at the University of Wollongong, Australia, and the ARC Center of Excellence for Electromaterials Science. Today, I will share with you our research work on the position control of 3D printed soft fingers with integrated soft pneumatic sensing chambers at the third IEEE International Conference on Soft Robotics at Yale University. The research objective of this work was to develop soft monolithic fingers that can be 3D printed simultaneously with soft pneumatic sensing chambers that can be used as position sensors for real-time control in various soft robotic applications, including soft grippers, soft robotic hands, and soft prosthetic hands. The first step was to design and model the soft fingers in a way that they can be 3D printed using a low-cost and open-source fused deposition modeling 3D printer. The 3D printing parameters were optimized in the slicing software to obtain functional prototypes with embedded airtight soft pneumatic sensing chambers. In addition, in the same design process, we characterized the soft material used to print the fingers to assess its stress-strain behavior and to develop a hyperelastic material model for use in finite element modeling. Finite element simulations were performed to predict and optimize the performance of the soft sensing chambers prior to their fabrication. Finally, we characterized the fingers and their embedded chambers before using them in real-time control experiments. The sensing chambers embedded in the finger are used to measure the bending angle of the flexure hinges. The figure on the right-hand side shows that each joint has a sensing chamber that is connected to a solid analog air pressure sensor, which is used to detect any volume change, or in other words, to measure the pressure change when the hinges are bent. The hinges and their soft chambers were optimized to obtain a linear relationship between the input mechanical deformation or displacement and the output pressure. A commercially available soft thermoplastic polyurethane or TPU known as NinjaFlex was used to 3D print the soft fingers and their embedded chambers. The hinges and their embedded chambers were optimized using finite element modeling to obtain the desired linear relationship between the input deformation and the output pressure. The initial design resulted in a nonlinear relationship between the input and output, as shown in the top figure on the right-hand side. However, after several design iterations, a linear relationship was achieved, as shown in the bottom figure on the right-hand side. We performed highly nonlinear finite element simulations that included geometric, material, and contact nonlinearities in ANSYS Mechanical. Through finite element simulations, we accurately predicted and optimized the performance of the hinges and their embedded chambers before their fabrication. This approach is very effective to rapidly and efficiently design soft sensors that meet certain design requirements and to save time, modeling, and fabrication resources. A soft pneumatic sensing chamber embedded in a single hinge was characterized in terms of linearity, hysteresis, repeatability, drift over time, lifetime, power consumption, and response time. As shown in the top figure on the right-hand side, the soft chamber has a linear response with negligible hysteresis. This linear response means that the relationship between the input deformation and the output pressure can be obtained by using two experimental data points. Therefore, there is no need for an empirical formula that requires an experimental evaluation using a specific experimental setup to obtain and describe the relationship between the input and the output of each 3D printed hinge. In addition, the soft chambers have a consistent and very stable output signal, and they can sustain more than 100,000 activation cycles without failure and any degradation in performance. Finally, the analog sensors used to measure the pressure require only 13.5 milliwatts to operate and have a response time of 1 millisecond. To be able to control the soft finger in real time based on the feedback pressure data obtained from the soft chambers, a geometric model based on the flexion of the soft hinges was developed to obtain a relationship between the angular displacement of the hinges and the change in the length of the tendon. The finger is tendon-driven, and a brushless DC motor with an encoder was used to drive it, and proportional integral derivative or PID controllers were used to perform the position control experiments, where the control gains were tuned experimentally. First, a real-time PID trajectory control experiment was performed using the feedback data obtained from the encoder to validate the pressure model, as shown in the middle figure on the right-hand side. Then, another real-time PID trajectory control experiment was performed using the feedback pressure data from the model, as shown in the bottom figure on the right-hand side. In this experiment, the encoder's data was not used in the control loop. Instead, it was just displayed to verify the pressure model again. To assess the control performance of the fingers, other experiments were performed. First, a step response control experiment was performed as shown in the top figure on the right-hand side. The finger showed a robust response to a step input with a small percentage overshoot, short rise time, and short settling time. Then, additional real-time PID trajectory control experiments were performed at two different frequencies of 2 and 3 Hz to show that the feedback pressure data from the sensing chambers can be reliably used to control the finger at higher frequencies. The motor can still precisely follow the reference trajectory when the pneumatic sensor's measurements are used at high frequencies. Also, the encoder's signal accurately follows the pressure sensor's signal at high frequencies, which again verifies the accuracy of the geometric model. Usually, such frequencies are higher than what's needed for the control of soft grippers and soft robotic or prosthetic hands. Here we show some videos for the real-time PID trajectory control experiments based on the feedback pressure data at different frequencies. Please note that in these videos, the encoder's signal is just displayed and not used in the control loop. First, at 1.5 Hz. Second, at 2 Hz. And finally, at 3 Hz. To conclude, we have developed 3D printable soft monolithic fingers with integrated soft pneumatic sensing chambers that can be used as position sensors for real-time control. A low-cost and open-source fused deposition modeling 3D printer and a commercially available soft material were used to fabricate the soft fingers and their embedded soft chambers. The behavior and the performance of the soft chambers were accurately predicted and optimized using finite element modeling prior to their fabrication to obtain a linear relationship between the input mechanical deformation and their output pressure. Finally, the chambers were used to perform real-time control experiments based on their output pressure data. The control experiments proved that such chambers can be reliably used to perform real-time PID position control using such pressure chambers. These soft fingers are ideal for integration in diverse soft robotic applications, including soft grippers, soft robotic hands, and soft prosthetic hands, where position control is needed for a safe manipulation of delicate objects in dynamic environments. Finally, this work paves the way towards developing soft structures, actuators, and sensors simultaneously in one step using affordable and accessible additive manufacturing technologies. Thank you for your time and attention. If you have any questions, please do not hesitate to reach out.